In the first part of our video, we'll present a particular algorithm called grow-shrink. This algorithm is actually a constraint-based algorithm that is looking for relationships between the verbals or constructs using the partial dependencies. Could be partial correlation, or could be, in the case of categorical verbals, could be mutual information or other criteria.
So it's kind of, for me as a naive beginner, it's testing different association based on these partial correlations. And it's building a network of association for us, or representing a structure. And we here have a very nice feature. We can namely blacklist or also whitelist certain relationships that we are sure of or that we don't want to see in the structure that is produced. And in our example, we blacklist, as Anna has written here, blacklist arcs between specific constructs. So we know that there's a certain kind of sequencing, that certain things are antecedents of other things. So for example, usage of a technology is a final outcome. We know that, and we are interested in explaining this or predicting this. So we are sure that this is kind of a dependent construct and not an antecedent. And that is what we, for example, blacklist here. Anna, am I right?
Exactly. So I have executed this line of code where we can see in a matrix which are the relationships that we blacklist. Actually, the edges between, for example, use, which is our last dependent verbal, and behavioral intention, between, again, use and facilitating conditions. So these edges will be forbidden or will be blacklisted in the network. And of course, similarly, we can whitelist relationships that have to be there according to, let's say, a theory or a theoretical background. So we can inform previously the algorithm about the relationship that can be or must be by defining this list.
And this is, of course, a very interesting feature, especially when we think of the combination with structural equation modeling, because very often we are not interested in completely exploring a data set, but we have some previous knowledge and might just be interested in finding some of the structures where we really are interested in the exploratory part of the algorithm. So this step is basically a pre-step where we feed the algorithm with prior knowledge that we have from our conceptual thinking.
Just mention that it's an optional step. If we don't have any idea about the possible relationships in the data, we can just exclude this step from the part of the code and just run the algorithm. Yes.
And that would be the next step that we have here on the screen, that we are actually running the algorithm. And when I first saw it, I was quite surprised, I must admit, how easy the code looks. I was always imagining that we have many lines of codes to run a machine learning algorithm, but what we see is just 3 lines with a few things that we need to think of. And Anna, what do we see here in the code?
Yes. So it looks very simple, but actually behind this function GS, which comes from grow-shrink, the name of the algorithm, there's a lot of parameters, right? There's a lot of code that we don't see. But it's simple indeed to program. We can just define the data set that we are interested in modeling. Of course, we have to select those variables that we are interested and create, let's say, a sample of our data set that we are going to model. The test, that means the statistic that will be used in identifying these relationships. In this case, we have partial correlation. We have continuous verbals, so that will be the test. We define, as I said, optionally the blacklist that we are interested, or the whitelist, and the level of significance in order to identify or to discover this structure. The software will apply a test, and we look at the significance level associated with each of these tests, and will display only those relationships that are significant at this level of significance.
And that's all the magic. I mean, this is how the algorithm produces a structure for us. And maybe we should run it, Anna, to see what the outcome is.
Okay, the algorithm has run. Now we want to visualize it. We can visualize it with a normal plot function in R, but in this case, we will use Gravit's plot, which comes from the Gravit's library. And it allows us to see the structure on.
Yeah, and this is quite fancy, what we see on the right-hand side of the screen. When I was first seeing this, I was very impressed because what we get is now kind of an overview of all the relationships between the different constructs in our model. of course, following our prior information that some associations are blacklisted. And we see two different things. Anna, we see some relationships with an arrow, and we see some relationships we don't see an arrow. So it seems to be some with a direction and some without a direction.
Indeed, some of the relationships are undefined because the algorithm could not establish the direction of, let's say, causality. So it's the role of the researcher to decide in which direction these edges go. With respect to others, for example, there might be some relationships, but the researcher might in the end decide to change the direction if, let's say, it doesn't make sense from a theoretical point of view. But at least it gives us a first indication of a possible relationship between these constructs. And what is most important to mention is that these relationships are based on partial correlations. So the algorithm is looking in the data at the conditional dependencies and is creating a network that is faithful to our data.
So this is really the thing that is, for me, very amazing. We have here a model with a few constructs, I would say, but we also have several applications in our research where we have many constructs and we are really not sure about the specific association. So this can really be helpful for us to get a first understanding what are really relevant relationships in the data set and in the modeling that we see. And in our paper, you will see that later, that the structure that we produce here is actually quite good if we compare that to many of the models that are out there in the market. So it's quite impressive how good the algorithm is producing something that is very close to conceptual models that we find in the literature.
One important thing is that this structure is just informative, right? It's just inspirational. It doesn't mean that it fits to the, let's say, true causality in the data, but at least it can inform the researcher about possible relationships then that can be tested and then reflect upon also from a theoretical perspective.
Yeah, and this is maybe important to mention that we always have to engage in something, some theorizing stage, that we talk about what is the mechanisms and what are arguments actually for these relationships that the algorithm has produced. But nonetheless, I think it's a quite helpful tool set here for us. Great. This was the first algorithm that we present. In the following video, we will present a further algorithm, and we will also present some criteria how to evaluate the quality of the structure that we have generated.